my last video, I explained Kepler's laws. Kepler's laws were able to explain planetary motion, but it could not explain the forces responsible for that. It was Sir Isaac Newton who explained the forces responsible for that using Kepler's laws and Galileo's observation. Now let us see Newton's universal law of gravitation. Here there are two masses m1 and m2 separated by a distance r. Newton's universal law of gravitation states that mass m1 attracts the mass m2 with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance. So this is a force acting on the second mass because of the first mass. It is directed towards the first mass. So r cap is a unit vector from first mass to second mass, but force is opposite. That's why minus r cap. This is a force on the first mass because of the second mass. It is directed towards that side. So it will be opposite to the force exerted on the second mass because of the first mass. So it's an action-reaction pair. The force exerted by sun on the earth is towards sun. So because of this attractive force, earth is moving around the sun. Now force exerted by earth on the sun is directed towards earth. It's an action-reaction pair. Now it obeys inverse square law. So here distance is marked along the x-axis and force is marked along the y-axis. So you can see as the distance increases, force decreases. Now let us see the torque experienced. Torque is r vector cross f vector. R cross f. For f we can substitute this. Now here r vector cross r cap. So the force is acting along the line joining. So here r vector r cap. So if two vectors are parallel, cross product is 0. That means torque is 0. Torque is dl by dt. Now torque is 0. That means L is a constant. Angular momentum is a constant. In the application of Newton's universal law of gravitation, we made an assumption. Both sun and earth are assumed to be point masses. It's a good approximation. Sun is a large body, but the distance between sun and earth is very large. So this is a good approximation. Say very large mass, earth also large mass, but the distance between sun and earth is very large. So it's a good approximation. We used the assumption, the point masses, both are assumed to be point masses. Here distances is very large. The distance is very large. Now point mass can be used even when distance is not large for a special case. For example, a hollow sphere of mass m and a point mass of small m. Now this mass can be assumed to be concentrated at the center of this sphere, can be considered to be a point mass of capital M, which is concentrated at the center of the sphere, then point mass. So here distance is not large. In this case, sun and earth distance is very large. So it's a good approximation. This is a special case. It's a hollow sphere. It can be assumed to be concentrated at the center and it's a point. It can be treated as a point mass. It's a special case.